So with just polar coordinates and Cartesian coordinates under our belts at this point, we can actually introduce an idea that's fairly central to doing modeling work, and I think often is not really dealt with very well in a lot of mechanics classes, and that's the idea of actually choosing an appropriate coordinate system for the problem that you're trying to solve or the system that you're trying to model, and not limiting your choice only to polar coordinates or Cartesian coordinates, but actually choosing what's called a natural coordinate system, or actually I should say what I call a natural coordinate system, because I don't actually know if this is something that is a common piece of vocabulary or not. And you've actually seen various examples, and you've done this before when you've chosen coordinate systems in the past. Um, but there's a way to sort of generalize choosing a natural coordinate system to systems that are a little bit more complex. So what do we mean by a natural coordinate system? So what is this? One of the things that a natural coordinate system does is that it enforces constraints in the problem. So by choosing your coordinates properly, you can actually constrain the system to act in particular ways. And one good example of that is if you think about a pendulum, right? And you're interested in knowing how the location of the bob on the pendulum moves. Well, pretty clearly you could talk about this location of the bob as having an x coordinate and a y coordinate. But when you say x and y tells you what the location of the bob is, there actually is a sort of implied constraint is that x and y can be anything they want to be so long as the value of x and y keep the length of this string being the same, right? On the other hand, you could also choose to use a polar coordinate system to describe this. You could say, okay, I'm going to define this angle as being theta, and I could say that in fact theta alone tells me the position of the bob so long as I know what the length of the string is. So in this particular case, choosing a polar coordinate system where the only thing that's actually changing is theta is a much more sensible choice because it enforces the constraint that the bob has to stay a distance L from the origin. If you were to choose x and y, on the other hand, you would need to actually include in the equations that you dealt with an equation that said basically x squared plus y squared has to be L squared. So you would need an additional equation. You end up getting two variables you're dealing with, and then you get one additional equation which allows you to solve for those variables. It's a whole lot simpler to choose your coordinate system in the first place to actually enforce these constraints. A second thing that a natural coordinate system does is it often encodes what you might call the sort of natural directions of the system. And you've certainly seen examples of this before. For example, you've probably dealt with in AP Physics, I would imagine you solve problems involving blocks on ramps, right? And you say, okay, well, there's a normal force here, and there's a gravitational force that's acting on the block, and so on. But the natural direction here is one that, if you actually think about two coordinate systems here, one coordinate system is one that says this is the y direction, this is the x direction, right? That's one that encodes the constraint that the block has to stay on the ramp. So that's a natural coordinate system from that perspective. But the other reason why it's a natural coordinate system is that one of the forces in this, the normal force, is in the y direction. So in this particular case, you could say this choice of coordinate system encodes one of the natural directions, the direction of the normal force, and also enforces the constraint that the block has to stay on the ramp. If, on the other hand, I chose this coordinate system, that coordinate system would encode one of the natural directions in the system, that is the direction of the gravitational force down, but would not enforce the constraint that the block has to stay on the ramp. So I would say that this choice is more of a natural coordinate system because it both encodes a natural direction and it enforces constraints. So before we go on to examples that are not just straight up polar Cartesian examples, let's do a couple of other examples of that. And the first example I want to do is actually one that raises a sort of question. So it's one you've seen back in ModSim. It's the extensible pendulum example. So here we've got a pendulum, but it's a pendulum that's on a spring, right? And so since it's on a spring, this distance can change, right? The location of the mass can change. In fact, this mass can move around anywhere in space. So what's the natural coordinate system for this? Well, if we think about encoding constraints for this, there actually aren't any constraints other than our assumption that it's staying in the xy plane. But this bob can, in principle, go anywhere in space, and I mean, we might actually encode some constraint that says the bob can't go above this level, but there really aren't any constraints. The bob can be anywhere in this plane. Okay, so that doesn't help us very much as far as choosing a natural coordinate system. What about natural directions? Well, there are really two interactions that we'll think about in this, and we're not really up to thinking about interactions yet, but you probably know what they are. One is the gravitational force, right, which is down. And the other is the spring force, which is acting along the spring, right? And if I call this the origin, which is one of the things you have to do in defining a coordinate system, of course, is decide where your origin is. If I call that the origin, the spring force is a radial force, right? It always is pointing away from the origin. So for this particular case, you might actually say, you know what, there is not one natural coordinate system for this. In fact, based on everything that I see here, I could choose a Cartesian coordinate system for this. Or I could choose a polar coordinate system for this. And there's not a whole lot of benefit one way or the other. Now, if you compare this with these other two earlier examples, pretty clearly for the pendulum case, in the pendulum case, the polar system enforces the constraints. The two forces, one is radial, it's the tension of the string. The other is vertical, it's the gravitational force. So polar would be the natural choice here. And in this particular case, pretty clearly a polar coordinate system isn't going to buy you very much. A Cartesian coordinate system that's oriented along the plane is probably the right one. So we've got three examples here. One of the things that is a characteristic of natural coordinate systems is that natural coordinate systems have the smallest number of coordinates necessary to capture to describe the system. And so one of the ways that you can see that polar is the right choice for this, for the pendulum case, is in the polar case, the only coordinate you need to describe the system is theta. Of course, you also need theta dot. You need to know how fast it's moving. But if you want to know where the pendulum is, you just need to know theta. Similarly, in this case, the case where the Cartesian system is oriented along the plane, the only variable you need to know is x. Right? So the choice of this Cartesian along the plane and polar in this case each give you a single variable that you need to keep track of, or two state variables, actually, theta and theta dot in this case, x and x dot in this case. Whereas if you were to, in this case, choose the Cartesian coordinate system, you'd end up having four state variables, or two sort of position variables, x, y, and then the velocities x dot and y dot. Similarly over here, in this case, you're going to need to have two position variables because the spring could be any length, and the spring could also be at any angle, so you would need both r and theta, or the bob could be at any x position and could be any y position. You need both x and y, and that's actually why, in this case, the Cartesian and the polar really kind of come out in the wash.